A exists. Yes, A exists. Okay, so now I can go to this one, right? But there is another thing. We actually have to find the biggest one from that. But what we'll do is A exists. Yes. A B exists. No, it does not exist. So we'll make current is equal to $8. Okay. And then from here we will check, does $BA, is $BA a child of this? No. So we'll create BA dollar. Create a BA dollar. Okay. So this got done, this got done, this got done. ABA.
ABA also got done.
Huh?
ABA also got done.
ABA got done. Yeah. AABA. So we find A. Yes. So AABA dollar. Right? We found A. Yes. We move the current to here. Do we find one with BA dollar? AB. Next, do we find something with A? A or AB or ABA? Anything. We found. Did we find something with A? No. So we'll create ABA dollar. ABA dollar got done. I don't know. This is actually the first time I'm doing it, so I don't know if this will match that one. If not, we'll change. Okay. BA dollar. B exists. BA exists. Right? So we'll remove BA. Rest remaining is ABA dollar. ABA dollar exists? No. ABA dollar. Okay? This went away. So we did this. ABA dollar. A will remove that. BA will remove that. Now we are at here. And then ABA dollar. ABA dollar. Is this the same? I don't know. So dollar and A dollar is, yeah, this is fine. And then, yeah, I think this is the same. So that is how you would do it. Yes, sir?
चुप करने के लिए बोला है बच्चों
I was doing this for the first time actually, really first time. So मेरे को थोड़ा.
Ashish, can you come on this
Okay.
last thing again?
Last thing, okay. So the last one was ABA dollar.
No,
right?
no, the last substring.
Last substring is ABA dollar, right?
Means like last case you just explained. Last substring.
These are all the substrings.
नहीं जो भी last सबने ऐड किया ना.
ABA, yeah, that's what I'm explaining. So ABA, ABAK, this K, right? We found first one.
Okay.
Did we find A? Yes. Forget about the dollar right now. We find A? Yes. We remove A.
Okay.
Do we find B? Yes. We find a B. Okay. We actually find a B and then we look for BA. Did we find a BA? Yes. Okay. So we'll remove BA, but there's no matching after that. The dollar came. So we'll say now the current becomes over here. So current is over here. After that we'll check A. This was not there. So we'll check, does A exist? Nothing exists. So we'll just create whatever is the rest, which is ABA dollar. Yes. Everybody understood this? Yes? No? Easy? Difficult? I don't know.
Medium.
Neither?
Medium.
Medium. That is what I actually want to hear. If anybody in an interview is asked a suffix tree and you coming before the class, if you did not understand what a suffix tree is and you right now you are saying medium, that is a success. At least for me. I think.
Yes, it is.
I think it is. Because suffix tree, I also was never, I never implemented suffix tree in my entire engineering or my.
Before you erase, this is the most efficient. Actually.
This is not the most efficient. Yes, I was actually going to thank you.
It's like 4 nodes or something.
Yes. So This is 1, 2, 3, 4, 5, 6, 6 nodes. 6 and 7. 1. This is also 7 nodes. This is 7 nodes. But the thing is, like, this is just 6 characters. But when you actually increase the number of characters, like 400, 500, the number of strings which are in here will actually start increasing. So the number of strings over here will be A, B, A, B, A, B, A, B, A, B, A, B, like this big. Do we need to store that much? I don't know. Maybe not. So what we do is, instead of that, we will start creating a substring. So I actually forgot right now, but like I'll tell you. Okay, so when a dollar comes, so dollar comes, what is the index of dollar? It is
Length.
yeah. So length and the length of this string is a dollar.
Okay.
So instead of a dollar, we can actually write 0, 1, 2, 3, 4, 5, 6, comma 1. Okay?
6 comma 1.
6 comma 1. So 6 comma 1 represents in this string index 6 and length 1. Okay. Next comes a dollar. A dollar would be
Index 5th and length 1.
5 length 2.
Length 2, okay, yes.
So we can write 5 comma 2. Okay. Next comes 5 comma 2 was a dollar. This, right? And but this BA was, where was this BA?
This one.
This BA was here. This one.
Yeah.
This BA was this one. So we will write instead of this BA dollar.
4, 3.
Okay.
Yeah. 4
3.
comma 3.
Are you talking about the other one?
The other BA.
Oh, sorry.
Yes.
Yeah. 4 comma 3. This was BA dollar. Okay. So similarly, this will actually be converted into everything. So these will go away and these will be just the index and the length. So the length of your suffix tree will reduce even more.
And
in that.
then would we store it in like a hash table or something?
You can do optimizations based on that. But like what I was looking at like if you create a 500 character long, so it basically goes up till, I don't know, more than 100, 200k nodes and stuff like that, which is too much. So that's why we actually need to compress it even further. I don't think they will actually ask you into that. You can mention that you can actually optimize it further using this approach. That is what you can say. But
So
yeah,
why
this
do
is
you consider this
Yeah,
an
push me
optimization?
optimization, because if it is, let's say it is 500 characters,
Yeah.
right? So instead of writing B
पर मैं तो नहीं पढ़ी सही
dollar,
नहीं
we can write 5 comma 1 2 3 4 5 6 7 5 comma 7,
It's just notation.
just a notation. And then like, because we already know this entire string 5 comma 7, we don't have to write it and store it every time. We can just go 5 comma 7, which means fifth, and take the length 7, take that substring out whenever we need it, because we don't need it every time.
Okay, so how do this will change the finding of
The structure, so the node structure will be struct a suffix tree, and then instead of a string over here, we will have an integer I start and an integer length, and then vector of a suffix nodes star children. Okay, so that will be the structure for the node instead of a string over here. So in tries we will have a character. In suffix tree we will have a string. In suffix tree modified, we will have an integer start and integer length. This will take much smaller length than the entire string.
Ashish,
Yes.
if we take on this approach, then if we want to find any substring in the string given, so how do we find it?
I like that was I was just reading this online, and I actually have not thought about it. Like
This approach we can only implement for the repeated character, repeated strings. Not first time we need to implement that character, every words there. Then we can check how many times it is repeating and compare.
we will see. Like I haven't.
I mean, only implementing through
Yes.
this way, you can't do anything.
Okay. I
But
will.
this will not be efficient way to search for a repeated character.
Yeah,
Yeah,
that
but
is
this
why
will be-
we have to do the mixing
Yes,
of both the
yes.
things.
But this will be efficient way to implement a phone book or a try.
Right.
Yeah.
Or
Okay.
what is that?
So
such kind of like
I will
Sorry, Sanjay,
add,
okay.
write the code for. Can I erase this?
Yeah.
Okay. I will write the code for suffix tree. So class a suffix tree. And I actually have not run this code. I just wrote this code. So I've not it compiles. I haven't run it. So I have to. There are bugs in this. So a suffix tree. And who is writing the equivalent of this? Come on. You write it. So what I will do is, like, I know that this is not complete. So I will send tries to you. You will write it in C#. I'll send who will take the suffix tries.
okay, okay.
You will take suffix tries, and you will take suffix trees. Okay. Do you want to take something?
Yeah, I can take whatever, tries of trees.
Take a suffix tree.
Tree.
Suffix tree, and you will write it in C#.
So the implementation of the suffix tree.
Implementation
structure.
of suffix tree class. Write a class of suffix tree. Add these ABA, dollar, and see if it works or not. My suffix tree implementation is not complete yet. I will make changes and stuff, and I'll send it to you.
Okay.
And I'll send whatever I have. I'll send it in C++, and you guys change it into C#.
And you're writing the suffix tree, right?
Suffix tree right now. The one this one. I'm writing this one right now. So string sg value. Okay. Tilde suffix tree. That is a destructor. Boolean is substring. String substring. Okay. And integer number of times. I haven't implemented these functions, but we'll see. So private colon structure a suffix node and string node value, and then vector of a suffix node star node. Okay, so this will be the structure, and we will have a root. So a suffix node star root. Okay, and then there is a suffix node star find node current y, suffix node current comma string value or something. So this will find a node. So if let's say if I'm here, I want to find ABA for this, it will go ahead and from the current it will try to find that current. Okay, that, and there is a add string function. So let's not go over there. We'll just write the constructor and we'll go from there. I'll erase it. This code is written. I'll send it to everybody. So. Okay. So there was Travis Trees. Here's Suffix Tree. Colon A suffix tree string a s value sc value. So first I will create a root. So root is equal to new a suffix node and then root arrow value or string or whatever, I don't know, I don't remember what I did, is equal to blank. There's nothing in the value of the root, and yeah, then we'll do integer length is equal to the length of the string that we have passed, and if it is 0, we'll just add a $, to that one. I'm not writing the code for that one. So then we'll say string t is equal to sc value plus $. So we added a $, at the end of the string. Then we'll say for integer I is equal to 0, I is less than t dot length I plus plus. What we will say is string str to add is equal to t dot substring from length minus I comma I plus 1. So similar code like the previous one, we'll find the substring of like we'll find a suffix